need to check if tree is null or not null. Now, then you check the data type, okay, of the node. If the data type is operand, now operand is a constant that we define here. Operand and operator, they are the two constants that we define in this two defined statement. Okay. Now if the data type is an operand, then you simply return the value. Now the syntax here is that we have the data type in the tree node is an info record. Okay. And the variable of the type is called info. And within info, we have three names: data type, operator, and value. Okay. So to check the data type of info, okay, so it's info.data type. Now if data type is operand, then you simply return its value, so info.value. Now if the data type is an operator, then you need to first of all evaluate the left subtree. Okay, and get the return value. Save it to a local variable, D1 is the first operand. Then you evaluate the right subtree. Okay, save the results in another variable, D2, that is the right hand side operand. After that, okay, you find out what is your operator. Then you call a function evaluate of the given operator with the two operands, and then return that value. Now that's the evaluate function. Okay, it's basically the same one that we assume here. Okay, that we have an operator and two operand value. Depends on your program that which operator you want to support. Okay, the division, addition, multiplications, exponentiation, some others, whatever that you want to support. So is there any question on this example? Now this is one application, okay, of a binary tree. Okay, so now before we talk more about those traversal, then you know that, okay, why we are concerned about with those in-order traversal, pre-order traversal, and post-order traversal, because it can be used in different applications. Now, just now we have seen the recursive implementation of the in-order traversal. Now, next we'll see another implementations of the in-order traversal without using recursion. Okay, so this time we use a stack to help us to implement the in-order traversal. Now, in the in-order traversal, we start from the root. but the first label that we are going to output is D. Okay? So it means that we need to move down from the root to the leftmost descendant. Okay. Now, if we are doing this movement using recursion, then it means that the pointers to the ancestor, okay, or to the other nodes along the path are automatically saved in the system step. Okay, because every time we make a recursive call, okay, we have the parameters and the return address saved in the step. Okay, so those pointers are automatically saved onto the system step. Okay. Now, if we are going to implement the computation without using recursion, then we need to maintain our own step. Okay, so we define our own step. We won't use the system step, okay, for this purpose. Okay. So in this case, we define a step. Okay, and the step are used to store the pointers, okay, to the tree nodes. Okay, now this is the data types, okay, that we are going to store, okay, onto the stack. Now we start from the root. First, we need to move down to the leftmost descendant. So when we are moving down, we need to save the pointers onto the stack, because after we finish the traversal of the left subtree, we go back to the root and then we can process it. Okay, so we save the pointers. So we save the pointers to A, the pointers to B, the pointers to C, and the pointers to D onto the stack. Okay, now this is the initial phase, okay, of the non-recursive in order traversal. Now we implement this action in a function called traverse left. Okay, so we start from a given node and we receive a stack. We move along the left hand side, okay, the left pointers, and we push, okay, the pointers onto the stack while we are moving down until we cannot go further. Okay, now we start from the root, we push A, B, C, D onto the stack. Okay, and then we cannot go further. The while loop terminates. We make a return. Now we are, okay, at this point. Okay. Then once again, every time either you use a stack or queue to implement the traversal, your loop condition will be as long as that data structures is not empty. So it means that there are some nodes that you have not yet visited. Okay. So as long as the stack is not empty, now in the stack we have 4 pointers, A, B, C, D. Okay, D is the top element. Okay. Now as long as the stack is not empty, we take out the top element. Okay, now we take out the top element. Now this is our pointer P. P is now pointing to D. And we know that the left subtree of P has been processed. Okay. Then we are ready to process P. Okay. So we output the label D. Afterward, we goes to his right child and traverse left. Okay, now P, okay, the right child of P is a null pointer. Okay, so when you call traverse left, the while loop is not executed. It simply make a return. Okay, now it returns, we come back to the while statement. Okay. Then the next pointer we take out from the stack is the pointer to C. Okay, now the pointer P is pointing to C. Okay. We output the symbol C. Then we goes to his right child, traverse left. Okay. Now in the stack, okay, now we have the pointers to E, push onto the stack. And still we have A and B below it. And we come back to the while loop. We process E. Okay, so the next item we output is E. Okay, E does not have left and right child. Okay, so no other non-null pointer will be added to the stack. We come back to this while statement. While the stack is not empty, the next pointer we retrieve will be B. Okay, now we output P, goes to the right child of B, is null pointer. So nothing will be added to the stack. We come back to the while statement. Okay, now we retrieve A. Okay. Repeat now A goes to the right child of A, traverse left. Okay, now when we are traversing left from this point, we will push on to the stack, the pointer to X, Z, and U. And the next element you output is U. After it is Z. After you process Z, you will put back the pointer to T onto the Z. Then you will process T, and then X, and Y, and then you finish. You can also use a stack to implement the pre-order traversal or post-order traversal. Okay, the idea is similar, okay, but the difference will be depends on the definition. Okay, when you are going to push and which pointer to push first, and pre-order traversal is a bit easier than post-order traversal. Okay. Any questions on this part? Clear to you? You understand? You think you understand? Now, remember, last time we talked about this tower of Hanoi, right? We have a recursive function to output the move sequence, right? And this is another version of the move function. Okay, all of you say you understand. How about writing a non-recursive function to do the work? Without using recursion. Think about it. If you have the answer, then you understand. if you don't have the answer, you think you understand. Now you know you don't understand. Okay? Now you see that program structures. It's the same as the in-order traversal. Now you say you understand this non-recursive in-order traversal of a binary tree. Then you have a method to implement the Taylor hand noise using a non-recursive function. Now, before the break, we have seen a few definitions about the properties of the binary tree. Okay, now we want to implement a function to evaluate those properties. Okay, now the first example is to determine the height or the depth. Okay, they mean the same thing. Okay, the two words mean the same things of a binary tree. Okay, now this implementation is based on the first definition where the root is labeled at level 0. Okay, now if the root is at level 0, then what is the height of a tree with one node? 0, because the largest level number of any nodes in the tree is 0. Then how about for a tree that is empty? Okay, we don't have negative height. Okay, so by definition, an empty tree also have height 0. Okay, so in this sense, okay, when you say something, the height of a tree is 0, there can be two possibilities. Either your tree is empty or your tree only have a root. So this is one disadvantage, okay, of defining a binary tree where the root is at level 0. But this is according to definition. Now to evaluate the height according to this definition, okay, we use a recursive function. Now if the pointer that we receive is null value is equal to null value, then by definition the height is 0. The other base case is if the tree is not empty now, it's not empty, but it only does not have left and right child. Okay, then by definition this is also 0. Now if the tree is not say having empty left and right subtrees, then you will call the function recursively to find out the height of the left subtree and the height of the right subtree. Then you will return the value, okay, which is equal to 1 plus the larger of the left and right subtree height. Okay, the total of the two subtrees plus 1, okay, will be your overall height of the tree. Okay. Now, from this diagram, now when you write a recursive function to operate on a binary tree, okay, the way we look at it is a binary tree according to definition. If it's not empty, it has 3 components. the root, left subtree, right subtree. Okay? Depends on your computation requirements. Okay. You may process the root first, or you process the subtree first. Okay. Now in this case, to find out the height, okay, it is basically is a post-order traversal. Now to find out the height of this subtree, you need to first of all find out the height of the left subtree and the height of the right subtree. Then you can determine what is the height, the overall height, okay, of this tree. Okay. Now in recursive function, the first thing you do is you identify what are the base cases. The base case will be either your tree is empty or your tree only have one node. You don't have subtrees. Okay, then it will be your base case. If it's not the base case, find out the properties of the two subtrees using recursion. And then you receive the results and carry out the computations together with the root. Now, the next example, to count the number of nodes in the tree. Now, to count the number of nodes in the tree, if the tree is empty, then the number of nodes is 0. If the tree is not empty, then the number of nodes in the tree will be the number of nodes in the left subtree plus the number of nodes in the right subtree plus the root. Okay. Then if the tree is not empty, then the number of nodes in the tree is equals to the number of nodes in the left subtree plus the number of nodes in the right subtree plus 1. Now, once again, the way that you look at the tree is this structure. You have the root, the left subtree, and right subtree. You won't look at the tree in this structure. Now, you have the root. Wow, you have so many things on the left subtree. You have so many things on the right subtree. How to write your program? If you are using recursion, you are not concerned about what is the structure of the two subtrees. You resolve it by recursion. Okay, so you look at it in your current level of recursions, you consider about the root. Now you have something in the subtrees, then you are going to find out your answer about the subtrees using recursion. Until you hit a base case, then you have a definite answer, and the answer will propagate backward. Now this example is to count the total number of nodes in the subtrees. Okay, then the problem can be slightly modified to find out the number of leaf nodes in the tree. Okay. Now, how many leaf nodes in this tree? The number of leaf nodes in this tree is equals to the number of leaf nodes in the left subtree plus the number of leaf nodes in the right subtree. Okay. And once again, you have the base case. If the tree is empty, you have nothing. Okay, the number of leaf nodes is 0. If the tree is not empty, then okay, if you have only one node in that tree, then it means that it's a leaf node. Okay, then you have one leaf node in the whole tree. You have nothing else. Okay. Now, if the tree is not empty and has more than one node, then the number of leaf nodes in the tree is the number of leaf nodes in the left subtree plus the number of leaf nodes in the right subtree. Now if we want to make a copy, okay, of a binary tree, so when we say we make a copy, okay, we want to have another instance of the tree, but the new instance have the same data value organized in the same way, but the two instances are totally independent. Okay, they don't share, okay, any memory resources. Okay, so that means copying. Okay. Now to make a copy, okay, so in this design of the function, it receives two parameters: the new tree that you are going to create and the other tree that you receive. Okay. Now, if the other tree is empty, then you simply set new tree to null pointer. Finish. Okay, you have nothing, no data. Okay, to copy. Okay. Now, if the other tree is not empty, okay, then you need to start the copying. Now, to start the copying, first of all, you create the root of the new tree. And then you copy the data of the root node. Afterwards, you copy the left subtree and copy the right subtree. Now, one remark about the use of this new operator. Under what condition do we use the new operator? We use the new operator when we need to create a new node, and that node will be used later. Okay, in the test, very often I saw students have these two statements. You define a pointer variable P, create a new node, set P to point to that new node, and then in the next step, forget about this new node. I don't use it, or I don't care where you are. You assign another value to the variable P. Then the creation of this new node is redundant, and actually it is an error, because you ask the OS to give you some memory space and you never use it and you never return it to the system, because you already lost its address. You don't know where to find it anymore. Okay, you lost the address. Okay, it's just like you go to buy a house, you write down the address, and then the next moment you stretch the paper. No, I don't know where it is now. Okay, it is something that you will do? No, of course not, right? Okay, so you create a node only if you are going to use it. You put it into some data structures. Okay. If you need a pointer variable, you assign the initial value to it. You don't need to create a new node and then, okay, I assign another value to it. Okay. But I have to say that many of those students make these mistakes are not in this room. Okay, so they won't know, okay, why this is not correct either. Now, for this copy function, the design of the function depends on how you, okay, perform the parameter parsing. Now, in this case, in this version, we pass, okay, the parameter new tree by reference. Okay, because we are going to set new values to this parameter. Okay, so this parameter must be passed by reference. The other way to implement the function is that if you have a parameters part by reference, you can also revise your statement such that your function give a returned value. Okay, so instead of a void return and receive a parameter by reference, you can receive only one parameters and return the results. Okay. Now if you design your function this way, okay, then if the other tree is empty, you return the null pointer. If the other tree is not empty, you create the root, a new root. Copy the data. And then copy the left subtree of other and save the return value to the left pointer of P. The same for the right pointer, the right subtree. And then you return P. Okay, so there are two options, depends on how you organize your function interface. So let's take a break again. Okay, and